Hello deep learners, welcome to this second lecture of PyTorch Zero to Hero playlist where we are going to learn what are tensors, why they are so much useful inside PyTorch, what is the structure of a tensor, and lastly how we can code tensors in PyTorch. So we are going to learn everything in this lecture. So take a pen and paper, grab a hot cup of coffee and let's get started. Alright, so we know what's a scalar. So it's nothing but a single numerical value like 5, 2.5, 1.5, anything. And we also know what's a vector, right? It's just a one-dimensional array that stores elements in a list or in a sequence format. And we also know what's a matrix. So it stores elements in this grid-like structure or in this tabular-like structure. So we know all this, but then what's actually a tensor? So you can think of tensors as multidimensional arrays. So you can think of them as the generalization of all the things that we already know. So we know what's scalar. So our scalars, they are nothing but our zero-dimensional tensors. We know what's vector, they're nothing but a one-dimensional tensor. We know what's a matrix, they're nothing but a two-dimensional tensor. So you can see these tensors, they are multidimensional arrays and they can scale up to n dimensionals. Now in PyTorch, we work on different kinds of problems, like we work on tabular data, we work with images, with textual data, and all of these aspects, they require different kinds of data set, right? So our tabular data, it has its own format, which is mostly a CSV-like format. Our images, they are basically RGB images which are stored in batches. And we have text data where they are nothing but their embeddings. So all these different entities, they have different dimensions. So as per our tabular data, they're mostly two-dimensional data, right? Because it's a table or a grid-like structure. As per our images, they are three-dimensional data or a four-dimensional data when we have batches of them. When we are working with textual data or the word embeddings and the textual embeddings, mostly we are working with one-dimensional data or two-dimensional data. And the beauty about tensors is that everything can be represented as tensors. So starting from our scalars to our tabular data, to our images, batches of images, our textual embeddings, everything can be represented in terms of tensors. And that is the beauty of it. Like, we don't need different data structures for different kinds of problems. We just have one data structure, that is tensors, and we use tensors for all our problems. And that makes our work much more efficient. And not only that, but while building and training our neural networks, the parameters that we have in our neural network, like the weights and biases, even they can be represented as tensors. The loss which we calculate during the training, that can be represented as tensor. The gradients of our loss with respect to all the parameters that we compute while backpropagation, even that can be represented as tensors. So literally, in the training also, we are using tensors as the means of data structure for literally everything. So literally everything in PyTorch, starting from our data, to our model parameters, to the loss that we compute, to the gradients that we compute, everything, they have just one data structure, which is tensors. And that is the power of tensors inside PyTorch. Now in Python, we have a library called NumPy, which also gives us arrays which are much more optimized than the generic arrays. So valid question is, why not use NumPy arrays instead of PyTorch tensors? So simply put, you can think of PyTorch tensors as your NumPy arrays but with additional superpowers. Like number one, these PyTorch tensors, they can live on GPU, so that whenever any new tensor operation is being done, GPU is being utilized so that we are getting an instant speed up and the computations are being done lightning fast. And number two, These PyTorch tensors, they support autograd, which means whenever we have to compute the gradient of a tensor, we don't have to manually compute it, because PyTorch autograd, it automatically computes the gradients for us. So that is the power of tensors as compared to basic and normal NumPy arrays. Alright, so now that we know what tensors are, let's look at why they are so much useful. So first is the data representation. So I've already told this, but it's worth repeating that everything in PyTorch can be represented as tensors. So starting from our scalars, vectors, matrices, image data, textual data, our neural network parameters, our loss gradients, everything, they have just one data structure, and that is tensors. Next up, the GPU acceleration. So here's where the thing gets much more powerful. So once we have represented our data in terms of tensors, we can move these tensors to GPU, so that whenever any new tensor based operation is being done, GPU is being utilized and our computations, they start flying. And also all the tensor operations that were previously being done using CPU, because they are now on GPU, they can also take the advantage of GPU parallelism. So the training and inference is being done very fast, because we are scaling the training and our inference process across multiple devices and multiple machines, and that will instantly boost the whole process. Next up is the autograd. So this is another superpower of PyTorch tensors. So during backpropagation, we have to compute the gradients of our loss with respect to all the parameters of our neural network. And if we have to manually compute all these gradients, then probably it would take ages to train any neural network. But that's where the magic lies. So once our neural network parameters, they are all represented as tensors, they can work now with autograd, which means that during backpropagation, all these gradients will get automatically computed by PyTorch autograd, so that we don't have to manually sit down and compute these gradients. And that will make the training process much more efficient and much more feasible. And once we have our gradients, we can use any optimizers like Adam, AdaGrad, SGD, RMSProp to basically update our neural network parameters, making the whole training process very smoother. And lastly, compatibility with NumPy. So simply at any point of time, we can convert our NumPy arrays to PyTorch tensors and our PyTorch tensors to NumPy arrays. So we enjoy both of these worlds, and we are not just limited to tensors, or we are just not limited to NumPy arrays. So we can use both, and we can easily convert one form to the other form. And that's why tensors are at the heart of PyTorch, which makes it much more fast, efficient, and powerful. Alright, so now that we have a much more clear understanding of tensors, let's look at the structure of tensors so that we understand it much more better. Alright, so any tensor, it has four things. First is the n dimensions, second is the d type, third is the shape, and last one is the device. So let's talk about each of these aspects. So at the very first, we have n dimension. So this n dimension, it basically tells us how many dimensions of our tensor. So it tells us how many dimensions our tensor has. So you can think of it like this way. So suppose we have a scalar. So suppose this is a scalar. Suppose we have 10. So this is nothing but a 0 dimension. Therefore its ndim is nothing but 0. It has 0 dimensions. Similarly, our vector, so this is a vector, so it has only one dimension, this along this x-axis. Therefore, see, it is one dim, it is one dimensional. and therefore its n dimension is equals to 1, right? Now suppose we have a matrix, so a matrix looks like this, right? So it has two things, it has this dimension and it has this dimension, so that is why it is two-dimensional, right? And that's why its n dimension is 2. And lastly we have an RGB image. So an RGB image looks like this. So suppose I am drawing an RGB image of 256 cross 256. So here is what it looks like. So suppose I am doing 256 cross 256 cross 3. So this is the height, this is the width. Means this is 256 or the height, this is the width, so this is 256. And like this we have 3 channels, means this is the 3. So how many dimensions does it has? It has this dimension, it has this dimension, and it has this dimension. Therefore it is 3-dimensional. And that's why its n dim is equals to 3. Right? So basically this n dim tells us how many dimensions our tensor has. Right? And this is very important. So suppose our data is very simple like a scalar, it has 0 dims. And suppose our data is a complex, like we have a batches of images. Let's say that we have batch of 16 RGB images. Then its shape will be nothing but 4 cross 3 cross 256 cross 256. So this is one image. So this is one image. And like that we have 16 images. So this is nothing but a 4-dimensional data. So its n dim is 4. Right? So the idea is the more complex our data is, so this is the complexity of data. So the more complex our data is, the more dimensions or the more number of dimensions our tensors will have. So you can think of it like this way, right? If we had a scalar, it has 0 dimension. If it was a batch of 16 images, it has 4 dimension. Alright, now let's talk about the D type. So this D type is nothing but it defines what data type our elements have. And what are these elements? These are basically the elements that are present in our tensors. So suppose this is a tensor, so it is a one-dimensional tensor or a vector, then, and these are all the elements, then the data type of these elements is basically represented by D type, right? So for example, we have multiple D types. Like for example, we have an integer 32 which represents our int. We have a float 64 which represents double. We have float 32 which represents the normal float. We have bool which represents the boolean. Like that we have all these data types inside PyTorch. And the idea is that suppose we have a tensor like this we have a tensor, and basically it is a boolean tensor. So suppose here the values are true, false, false, true, false. Here also true, 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 false, true. Then suppose this is a 2D tensor or a matrix, and these are the elements. Then you can say that its D type is nothing but a bool. Why? Because the elements of these tensors, they are booleans, right? And that is why the D type of this tensor is boolean. It's that simple. So recap. So basically D type tells us what data type our tensor elements are. Alright, the third one is shape. So this shape is simple. It basically tells us how many elements we have. So it tells us number of elements we have along each axis or each dimension, right? So very simple. So suppose at first we have a scalar. So a scalar is like 10. So earlier we saw that a scalar's n dimension is 0 because it is a 0-dimensional data, right? So its n dimension is 0. So its shape is nothing but 1. Why 1? Because it just has one element, which is 10, right? Simple. Now let's say we have a vector. So a vector looks like this. Suppose it has 4 elements, 1, 2, 3, 4. So it is simple, it is a 1-dimensional data. So that's why its n dimension is how much? It's 1. But what about the shape? So we have just one dimension, and this one dimension is this dimension. So across this dimension we have 4 elements, right? This one, this one, this one, and this one. So that is why its shape is nothing but 4. It's that simple. And suppose we have a matrix or a 2D tensor like this, where we have elements over here, then its n dimension is 2 because it has 2 dimensions, which are, first we have this dimension and then we have this dimension, right? So across this dimension, how many elements are there? There are 4 elements or 4 columns, and across this dimension there are 2 rows, right? So that's why you can think of its shape as 2 cross 4, right? So it has 2 rows, which are this and this, and across each row there are 4 elements. So suppose this is one row, then across this row there are 4 elements, this one, this one, this one, this one. So that's why its shape is 2 cross 4. And lastly, let's say that we have an RGB image. So an RGB image looks like this. We have 3 channels stacked on top of each other. Let's say its height is 128 and its width is 128, right? And like that we have 3 channels because it is an RGB image. So it's, first of all, its n dimension is 3 because it has 3 dimensions. This dimension, this dimension, this dimension 1, this dimension 2, and this is the 3rd dimension. So that's why its n dimension is 3. And its shape is 3 cross 128 cross 128, where this and this represent the height and width, and this represents the channel. So that's how an RGB image is represented in terms of tensors. And lastly, let's say that we have a batch of 12 RGB images, where each of this is one image. Then it's like saying that we have this image, and on top of this we're stacking another image, and then we're stacking another image, and like that we're doing till we have 12 images, right? So it's like saying it's 4 cross 3 cross 128 cross 128, where this represents the channel, this is the height, this is the width, just like this. So if we had just one image, it would be represented like this, and if we had a batch of images, it would be represented like this. But at last we have this batch dimension, so it represents 12, so it will be 12 over here, right? So that is the whole concept of shape. And lastly, we have the device. So this tells us where our tensor is located. So this tells us where our tensor is located. So is it located on CPU or is it located on our GPU? And like that, whenever we are doing tensor based operation with this tensor, it will decide whether to use CPU or whether to use GPU. And this is very important because suppose we have 2 tensors, T1 and T2. For these 2 tensors to participate in a tensor based operation with each other, let's say that tensor based operation is like T1 plus T2, then for this thing to happen, these both tensors need to be in the same device. So either T1 and T2 can both belong to CPU, or T1 and T2 they are both located on GPU, right? But it can't be that T1 is in CPU and T2 is in GPU. So for tensors to participate in any operation with each other, they need to be present in the same device. Otherwise, PyTorch will basically raise an error and you will be confused that what that error is. So as a recap, any tensor has four things. First is the n dimensions, which tells us how many dimensions it has. Next we have d-type, which tells us the data type of the elements that are present inside that tensor. Next we have shape, which tells us how many elements are present across each dimension. And lastly we have device, which tells us where our tensors are located. Is it on CPU or is it on GPU? And together these four, they represent the structure of any tensor. So you have to be very clear with it. Alright guys, so now that we have a much clear understanding of tensors, let's stop this theory and start coding, because that is how things will become much more clear and intuitive. So open your Google Colab and let's start coding. And please don't just watch it, start coding alongside with me, because that is how things will really stuck. So let's go. Alright, so here I have opened my Google Colab and I've already connected it. So let's actually start. So at first, let's import the packages, right? So let's import. So first, for using PyTorch or for using tensors in PyTorch, we have to import the torch package. So import torch, and that will basically get imported. Alright, so now once we have imported torch, let's now see how to see the device that we're in. So are we using CPU or are we using GPU? So for that, first you have to create any kind of variable. I'm creating the variable as a device. So I'll create this device variable and I'll do torch.device CUDA, which is, or you can say the GPU, if torch.CUDA is available, else CPU. So what is this code? So it says torch.device CUDA if torch.CUDA is available, meaning the torch.CUDA is available. So you can think it like, is GPU available? If it's yes, or if this gets true, we return this torch.device CUDA. Otherwise we return this CPU. So at the end, this variable stores this device type of CPU, which means we are using CPU. Now if you go to runtime and you change it to T for GPU and you again rerun it, you will see that here it will come CUDA, right? So that is the concept of device. Alright, now let's see the different tensor creation methods. So let's look at the first method, which is torch.empty. So if I do torch.empty, and as you can see, we need to mention a size. So let me say that the size is 2x3. So you can see we get a tensor of shape 2x3, meaning 2 rows and 3 columns, right? And you can see that these are random values. So what torch.empty does is, at first we have a memory block where there are these junk random variables, and when we do torch.empty, we are allocating new memory space for this tensor in that memory block. But previously in that memory block, there were some random numbers present, right? So in this tensor, those random numbers are coming and they are being the elements of this tensor. Or you can say that the random numbers present previously, they are coming to this tensor and they are being a part of it. So that's why you are seeing these random junk variables. Next, let's see the torch.zeros. So torch.zeros, again the simple size, and if I do T, you can see we get a tensor of size 3 cross 5 because we mentioned here 3 cross 5. And what torch.zeros does is it initializes all the elements with zeros. So that's why you are seeing that all the elements are nothing but zeros. So that is what it does. Similarly, we have torch.ones, which does one initialization. So torch.ones 5 cross 6, if I do t print, you can see that we get a tensor of size 5 cross 6, and here all the elements are 1. Just like in zeros where 0, here we have 1. Now let's look at the rand method, which basically initializes our elements with random variables. So let's say I do t equals to torch.rand and I give a shape of 5 of suppose 3 cross 4. You can see all these elements are random variables from 0 to 1, right? So you can see its shape is 3 cross 4 and all these elements are ranging between 0 to 1. So this is what the rand method does. And let's see another trick, which is converting a vector to a tensor. So let's say converting a vector or a matrix or anything. So let's say that we have a vector this 1 2 3 4, right? Now how to convert this vector to a tensor? So the syntax is simple. We do first torch.tensor and we just pass this vector. So we just do vector, and if we print t, you can see that we get a tensor where the elements are nothing but these vector elements. So that's how you convert a vector to a tensor. And similarly, you can do the same with matrix also. Alright, now let's say that you want some values between a certain range. So let's say that I want all the even numbers from 0 to 50. So how is that done? So that is done using the torch.arange method. So torch.arange 0 to 50. So you can see the starting value is 0, the ending value is 50. But if the ending value is 50, it basically excludes 50. Means it runs from 0 to 49. But we want 50 to be included. So here we are going to do 51, right? So it's 0 to 50. And we have to give a step number. So let's say we give a step number of 2, we print t. You can see all the even numbers from 0 to 50. But if I did nothing, if I didn't mention any step, then by default the step is 1. So you'll see 0 to 50 all these values. And that makes sense, right? Now let's say that you want some values equally distributed in a range. So let's say that you want 10 numbers equally distributed from 0 to 100. Right? So for it we use torch.linspace. So torch.linspace, and the starting value is 0, the ending value is 100, but we want 100 to be included, so we'll do 101. And the steps is we want 10 numbers. Now if you print t, so if you print t, you can see this is what we are getting. Alright, I think this 101 is included. I'll do 100. And you can see these are equally distributed. Next, let's say that you are doing some maths and you want your diagonal matrix like I2, I3. So for it, we use the torch.i method. So torch.i, and we basically mention the n like I2. So if I do I2 and I print it, we get 1001. Similarly, let's say you want a I3 matrix. You just specify 3 as n and it gives 100, 01, 0001. So that's how you create your identity matrices. Now let's say that you want a tensor where all the elements are just one single value. So let's say torch.full. So first we have to mention the size. Let me say that the size is 2 cross 3. And then we've mentioned the fill value, like what value to fill it with. let's say it's 5. So you can see that we get a tensor of size 2 cross 3 where all the elements are 5, right? So again, using it you can do this 0 initialization, 1 initialization, like you just mentioned over here your 0, so you get the torch.zeros method. If you mention here 1, you get the torch.ones method. So that's very simple. Also guys, let's see the structure of this tensor. So let's say we have this T tensor. Now let's look at the shape, the D type, the dimensions, the n dimensions, everything. So for shape, what you have to do is T dot shape and you get this size. So it says 2 cross 3. Now let's say you want the n dimensions. So you do torch.ndim and you get 2 because it's a matrix, right? So this is one dimension and this is another dimension, right? So this is 1, this is 2, and that's why 2 dimensions. Let's say you want to see the device. So let's say it's t.device. You get to see that it's in CPU. It's very simple. And lastly, let's say that you want to see the D type. You simply do t.d type and you get to see that it's torch.int64. So that's how you see the structure of any tensor. Alright guys, now let's look at another important concept, which is the like concept. So this is simple. So let's say that we have a random tensor of, let's say the size is 3 cross 4 or 3 cross 5. So this is the tensor. Now let's say that you want another tensor. Suppose you want that tensor to be a 0 initialized. So you use that torch.zeros method, but you want its shape to be the same as this tensor. So how do you do it? So it's very simple. You simply do torch.zeros, but you don't do zeros. Instead you do zeros like. And here you mention the input tensor. So it's T. Now you can see that you get a tensor which has been initialized with 0 because you're using the zeros method. But because we're using the zeros like method, its shape is same as this tensor. Why? Because in this function we're passing T, and this tensor over here T, it has a shape of 3 cross 5, and that's why its shape is also 3 cross 5. It's that simple. Now similarly like that you can do torch.ones like, which will give torch.ones like, which will give you a tensor of that same shape but initialized with 1. So that's the concept of it. And now let's say that you want to see the D type. So a.d type, A is this tensor. So you can see that it's data type, or the data type of the elements of tensor A is float 32, right? But let's say you want to change it. You want it to be float 64 or an integer. So for that you basically do A equals to A.2 and then you mention the D type. So you can see you just mention the D type. So for mentioning the D type, you use torch.float64. Now if you do A.D type, you can see that it's now float 64. So earlier we had float 32, then we did this, so it became now float 64. Now let's say you want it to be an integer. So again, the same, A equals to A.2, torch.int32, and then you do A.D type, you get torch.int32. So at first it was float 32, from there you did this, so you got float 64, then you did this, so it became int32. So that is how you can easily and very easily you can change the data type of the elements of any tensor. Alright guys, now it's time to perform some arithmetic operations. So let me give a title of maths, the most hated subject. So let's say we have this tensor, torch.tensor, Let's say we have 1, 2, 3 and 4 or 5. So we have this, I'm very sorry. So we have this tensor T containing 1, 2, 3, 4, 5. Now let's perform arithmetic operations. So let's say that we want 2 to be added with all these elements, right? So for that we simply do T plus 2. So it returns a new tensor where the elements are nothing but the elements of this added by 2. So it was 1, it has now become 3. It was 2, it has now become 4. So basically it returned a new tensor where the elements are nothing but these elements added by 2. So that is the concept, and it's very easy to understand. If I do T minus 1, so it returned a new tensor where the elements are nothing but these elements subtracted by 1. So similarly you can do T times 2, so it will do element wise product. So times 2 times 2, 3 times 2 is 6, 4 times 2 is 8. Simple. Similarly you can do power. So 1 cube is this, 2 cube is this, 3 cube is this, 4 cube is this, 5 cube is this. And please make sure that these operations are returning a new tensor, right? So it returns a new tensor. This is returning a new tensor. It is not updating this previous tensor, right? So if I do T, you can see the value is same as this, meaning that T plus 2, T minus 1, T times 2 and these operations, these are not updating my original tensor. Instead, they're returning a new tensor. So make sure that whenever you're doing operations like this, you always store them in a new variable like this. We have T and we want T plus 2, so we do this. So now A will become this. Similarly, you can do this arithmetic operations between two tensors. So let's say we have two tensors. So this is the first tensor T1, and let's say its values are 1, 2, 3, 4, 5, 6. So T1 looks like this, and similarly we have a T2 tensor whose values are 7, 8, 9, 10, 11, 12. So T2 is like this. Just like in scalars, we can do everything in a similar way here also. So let me say T1 plus T2. It returns a new tensor where the elements are the sum of elements of these. So it's the element wise sum of these two tensors. So 1 plus 7 is 8, 2 plus 8 is 10, 3 plus 9 is 12, 4 plus 10 is 14, like this. Like it's element wise sum. Similarly, if you do T1 minus T2, you'll get this, right? Similarly, if you do T1 times T2, you get this. Like these are all element wise products. So 1 times 7 is 7, 2 times 8 is 16, 3 times 9 is 27, and like that. And similarly, you can do T1 by T2, which will be obviously in decimals. So that is the beauty of tensors. And also make a note that these are returning a new tensor. So this is returning a new tensor. All these are just returning a new tensor. They're not updating the previous or the original tensor. So please make sure that you understand this. And another important concept is of dot product. So let's say we have two tensors. So we will be creating new tensors. So toss dot randend. So what randend is used is it is used for initializing random values in a certified range, and these are in integer. So let me say the low point is 1 and the high point is 5, and let me say the size is 2 cross 3. And over here you can also specify the d type. So d type is equals to toss.in32, Similarly, I do T2, and here I give the shape as 3 cross 2. So this is my T1. Alright, so T1's shape is 2 cross 3, and T2's shape is 3 cross 2. Now we want dot product, right? So dot product in PyTorch is done using the @ symbol, right? So if we do the asterisk, it basically gives us the element wise product, and this @ it gives us the dot product. So @ T2, and the reason why I did 2 cross 3 and 3 cross 2 is because if you do this, it will basically be nothing but 2 cross 3 dot product 3 cross 2, right? Now in dot product, we know that if this is the case, then the output tensor will be of shape 2 cross 2. So basically these two will get absorbed, and the output tensor's dimensions or the shape will be nothing but this cross this, right? So let's verify it. So I did T1 @ T2. You can see we get a new tensor where the shape is 2 cross 2, right? So that basically proves this concept. So if we have 2 cross 3 @ 3 cross 2, these both will get removed, or these both will get performed and will get computed, and they will get absorbed, and the final output tensor's dimensions or shape will be this cross this. Alright, now let's look at some more functions that torch tensor provides us. So I'm creating this tensor of -1, 2, 0, -4 and 5, and I'm returning this. So at first, let's see the torch.abs method. So what this torch.abs method does is, whatever our tensor is, it returns the absolute value, meaning if it's negative, it makes it positive. So you can see these are the absolute values, meaning that they are values without any signs. So -1 became 1, 2 became 2, 0 became 0, -4 became 4. Simple. Next we have torch.neg, which returns the negative of these values. So -1 became 1, 2 became -2, 0 became 0, -4 became 4, like that. Similarly, we have torch.round. So for round, let me take a new example. Torch.tensor 1.2, 5.6, 7.9 and 5.5. So this is the new tensor that I've created. Now let's say that I'm rounding it off. So torch.round. Now what this round function will do is, it will basically round off our values of our tensor. So 1.2 became 1, 5.6 became 6, 7.9 became 8, 5.5 became 6. So that is a simple concept. Similarly, like round, we have seal, we have floor. So seal basically does a rounding off only, but it prioritizes the upper limit. So for 1.2, the upper limit is 2, so it became 2. For 5.6, it's 6. For 7.9, it's 8. For 5.5, it's 6. Similarly, the floor, it does rounding off only, but it prioritizes the lower limit. So 1.2 became 1, 5.6 became 5, 7.9 became 7, 5.5 became 5. So you can clearly see the difference of seal and floor. Now let's look at the torch.clamp. So if I do torch.clamp and I mention the tensor t, and for the minimum value I give it as 5.5, or let me leave it to 5, and I make the maximum value as 6.5, then you can see that in my tensor, if any value is less than 5, that element will become 5, and if any value is greater than 6.5, that element will become 6.5. So it first came 1.2, so 1.2 is less than 5, right? So it became 5. Next 5.6, it comes in this range, so it is unchanged. Next 7.9, it's greater than 6.5, so it becomes 6.5. Next 5.5 comes in this range, so it's again 5.5. So that is what the clamp does. Now let's look at some more interesting methods. So for that, I'll first create a 2D tensor. So let me say it's 2 cross 3. Let me take it as 3 cross 3. So this is my 2D tensor. So in maths, we have a concept of determinant. So for calculating the determinant of any tensor, we can do torch.det. We mention that variable. So you can see it's 0.1212. Similarly, we can get the inverse of this tensor. So for that, it's just t, because our tensor's name is t, and we just do t dot inverse. Yeah, it's that simple. And also we can do transpose. So the t is this. Now if I do t dot capital T, so it transposes. So the row becomes column and the columns become rows. So you can see these values 0.26, 0.75 and 0.93, it came down over here, right? And these values, they became this, and these values, they become this. So the rows become column, column becomes row. That's the concept of transpose. Alright, now let's say that we have a 2D tensor. So torch dot randint, the low is 2 and the high is 7 and the size is 3 cross 5. So this is our tensor. Now let's say that you want the sum. So we basically do torch.sum. So what torch.sum will return is this sum of all these elements. But what if you want it to be row wise sum or a column wise sum? So for that, you do this, and last you mention the dimension. So in PyTorch, always remember that the 0 dimension means this one. So in PyTorch, always remember that we have two kinds of dimension, the dimension 0 and dimension 1. So dimension 0, so before that let me say that the t dot shape is 3 cross 5. So dimension 0 is this one and dimension 1 is this one, right? It's that simple. So dimension 0 basically specifies rows and dimension 1 specifies the columns. So if I mention torch.sum and dimension equals to 0, what it will return is the sum of these elements, 3 plus 3 plus 5, and then 3 plus 2 plus 6, and then 3 plus 6 plus 3. So let's see. Yeah, so 3 plus 3 plus 5 is nothing but 11. 3 plus 2 plus 6 is nothing but 11. 3 plus 6 plus 3 is nothing but 12, right? So it's row wise sum. And if you want the column wise sum, it is dimension 1. So you got the sum of this over here, you got the sum of these elements over here, you got the sum of these elements over here. It's very simple concept. Similarly, we have torch.mean and we have torch.median. Alright, so our mean just returned an error. It is saying that the input data type must be either a floating point or a complex data point. But what it got is long. Alright, so let's debug it. So in the torch.mean, we are passing t. Now t's data type is int64, which is long, right? But it's saying that the input data type must be a floating point. So it can't, so this mean method is not feasible with this, but it needs the floating point. So we can simply do t.to, meaning that we are converting our long data type to our float data point. So t.to torch.float32. Now if we do this, it will run, right? And similarly, let's see, yeah, the median is working fine. So I hope that you understand what the error was and how we debugged it. And similarly, you can also mention here the dimension so that you get the row wise mean and the column wise mean. And similarly, you can do that over here also. And like that, we also have the torch.max method and the torch.min methods, which return the maximum value and the minimum values. So if I pass the tensor over here, you can see the maximum value is 6. If I pass the minimum value, or if I do the torch.min, it returns 2 because the minimum value is 2. And also you can mention here the dimension so that you get the row wise max and the column wise max, right? And you can do that in min also. And similarly, we have the torch.argmax. Let me say the dimension is 1. So what it does is, basically, because dimension equals 1, it goes like this, then this, then this. So first it got this, so it does argmax, which means it first finds the maximum value, which is 4, and then it gets the position or the index of this value in this row. So it's 0, 1, 2, 3, and that's why you got 3. Next, this row, so the maximum value is 6, so it gets the first index of 6, so it's 0, 1, 2, and that's why it got 2. And lastly, over here we have 6, so it's 0, 1, and that's why we got 1. Similarly, you can do the torch.argmin. So the minimum value is 0, so it's at the 0th index. The minimum value is at the 1th index, so it returned 1. The minimum value is over here, so it's 0, 1, 2, 3, 4, so it returned index 4. Similarly, like mean, we have torch.standard deviation. So it gives us the standard deviation of this. Alright, again, so standard deviation and the variance method, they are accepting only floating points, whereas our t.d type, it is long, or it is in 64. So again, the same solution, it's t.2 torch.float 32, and boom, that will work fine. Similarly, we have torch.var, which returns the variance of this tensor. So here it goes. Alright, now let's say we have two tensors, t1 and t2. So t1 is this, t2 is this. Both are of shape 4 cross 5 and they are being random initialized. So we can compare the values of these two tensors. So we can say t1 is equals to t2, and it will return a new tensor with boolean values. So what's happening is that it is comparing individually of these elements with these elements, and wherever this condition is satisfying, it is returning true, else false. So 6 is equals to 6, hence it's true. 4 is not equals to 5, hence it's false. 4 is not equals to 3, it's false. So I hope you got the idea. It does element wise comparison, and then you get a boolean value for each of these elements. Similarly, you can do t1 is not equals to t2. You can do t1 is greater than t2. You can do t1 is less than t2. But you can do t1 is greater than equals to t2. And similarly, you can do t1 is less than equals to t2. So that is the whole logic and the power of tensors. You have so much flexibility. Alright, now let's see how to copy a tensor. So let's say we have a tensor t1 with this. Now suppose you want to create a new tensor. So let's say you do something like t2 is equals to t1. So t2 is this. But the problem with this approach is that if you check the ID of t1 and t2, it is the same, which means that t1 and t2, they are not copies. Instead, what they are two different variables which are referring to the same memory block, right? Which means my t1 is this and my t2 is this. If I do t2 of 0 is equals to 4, then although my t2 will become 4, 2, 3, because I'm changing the first index and then making it as 4, but my T1 will also change. So that is the problem. Now how to solve it? So again, I'm creating a new tensor T1. So to solve it, we basically do T2 is equals to T1 dot clone. And that's it. And now if you check the IDs of T1 and T2, you get to see that they're different. Meaning that if my T1 is this and my T2 is this, now if I do this operation and I again run it, you can see that only my T2 has got updated and not my T1. So that is how you do it. So you use this to copy a tensor. Next, let's look at some more functions. So we have T1 as this. We have torch.log, which basically returns the logarithmic values of these elements. So torch.log of T1 returns this. Similarly, we have torch.exponent, which returns the exponential values of these elements. So T1. Similarly, you can do torch.sqrt, which returns the square root values of T1. You get this. So now that we have T1, let's say that you want to check its device. So we do this and we see that it's in CPU. Now let's say that you want it to be stored in GPU. So how to convert it? So again, you use the same .to method, right? So over here, you mention the device as your CUDA, and that will simply return an error. Why? Because I'm not connected to the T4 GPU. So you just get connected to it and check it once, and this will basically get converted to GPU. And lastly, let's look at the manual seed. So let's say that you want to create two tensors which are randomly initialized, but you want them to be initialized with the same random numbers. So basically what I'm saying is torch.rand, if I do the size as 5 and again I do a new tensor and I do this 5, then T1 and T2, you can see that they are different because they are being randomly initialized, but you want their values to be initialized with the same random numbers. So you do that with manual seed. So what manual seed is, you can think of it as the controller of the randomness. So manual seed is nothing but it controls how much randomness you need. So here how it works. You first mention the torch.manual seed. Let me say the manual seed is 15 or any integer, and then you create this tensor. Alright. Now in the same method, specifying the same manual seed as 15, you create your new tensor T2. Now if you do this, you're going to see that they're having the same numbers. Why? Because when you're mentioning this, you're telling your PyTorch that, hey PyTorch, I want this randomness value, or I want 15 as my randomness value. Similarly, if you do 15 and you do 25, you're going to see they are different, obviously, right? But if you do 25, you're going to see that they're going to be the same. So that's the simple concept of manual seed. Alright guys, so that's Tensors simplified for you all. I've linked down the code slides, the Google Colab, and also I've given an exercise based on tensors which will make your understandings much more better. So please go ahead and solve that exercise so that your understandings they become much more clearer, and I've linked them all in the description below. So go ahead and check those out. And in the next lecture, we'll dive deep into AutoGrad, which is the magical engine which makes backpropagation much more beautiful. So take a break and I'll see you in the next one.